Imagine staring into the black, silent ocean of space and finding something that shouldn't be here. On August 6, 2025, the James Webb Space Telescope pointed its golden mirrors toward a faint moving dot and captured what scientists are calling a once-in-a-generation moment. For the first time ever, we have a clear, high-resolution infrared image of 3I/Atlas, an object that doesn't belong to our solar system at all. It came from somewhere out there, a completely different star. And now, it's flying straight through our cosmic neighborhood. Think about that. This isn't just another comet. This is the third confirmed interstellar visitor in human history. The first two were Oumuamua and Borisov. Both left scientists with more questions than answers. But this time, it's different. The image James Webb captured didn't just reveal a streak of light. It showed texture, structure, and chemical fingerprints that have never been seen in any known comet before. Astronomers could actually map its coma, the glowing cloud around its core, and detect strange signals in its infrared spectrum. Signals that hint at an origin billions of years and trillions of kilometers away. What makes this even more incredible is how early Webb picked it up. While most comets remain just specks until they're dangerously close to the Sun, 3I/Atlas was caught long before that. Its light was faint, but not random. It carried a pattern, a clue, like a cosmic fingerprint from another world. Behind the scenes, researchers described the moment as electric. One scientist said it felt like watching a ghost materialize out of the darkness. Because this object isn't part of us. It's a traveler from another system. And this is the first time humanity is truly seeing it in such stunning detail. The image is so sharp, so detailed, that it's already rewriting what astronomers thought they knew about interstellar comets. Its tail, the angle of its coma, even the brightness fluctuations, they don't behave like anything from our neighborhood. This is new territory, a mystery wrapped in ice and starlight. And here's where it gets even stranger. 3I/Atlas is not just passing by quietly. Its trajectory and activity suggest a complex story, one that started light years away. And Webb's instruments are capturing every second of it. Something this rare doesn't happen twice in a lifetime. This is the first real close-up look at a messenger from another star. But what exactly is it made of? Why is it glowing so early? And what secrets are locked inside its frozen heart? That's what scientists are about to uncover, and the answers could change how we understand the birth of entire solar systems. If you're loving this deep dive into 3I/Atlas, hit that subscribe button now so you won't miss the next incredible space discovery we uncover. When James Webb focused deeper into the spectral data of 3I/Atlas, something immediately stood out. It wasn't the shape. It wasn't the brightness. It was the smell of the comet's breath, its chemical fingerprint. Most comets we've studied in our solar system behave predictably. As they approach the Sun, the warmth kicks water ice into vapor, creating a coma mostly made of water. But this time, it wasn't water leading the dance. It was CO2, carbon dioxide, and not just a little. Webb's instruments detected 8 times more CO2 than water vapor. This ratio is unheard of. It doesn't fit the pattern of any known comet in our neighborhood. It's like meeting someone who breathes a completely different atmosphere. This is the first hard clue that 3I/Atlas was born far away, under conditions unlike anything around our Sun somewhere in another star system. There was a place where CO2 was more abundant, where frozen gases shaped planets and comets in a completely different way. 3I/Atlas is a time capsule, a frozen messenger carrying the chemistry of a foreign world. The data shows its coma is rich, thick, and highly active, but the water content remains strangely low. Scientists expected water to dominate at this distance, but instead, it's the CO2 that's forcing this comet awake while it's still far from the Sun. It's almost like it's defying the rules that govern our solar system's comets. Behind the scenes, researchers are stunned. Because if CO2 is the primary driver, it means this object formed in a colder region, possibly beyond the water ice line of its original system. It may have spent billions of years sleeping in the dark, perfectly preserved, until something launched it across interstellar space. Webb's spectral readings paint an even more mysterious picture. the CO2 isn't evenly distributed. It surges from localized jets, bursts of gas that flare like cosmic vents, hinting at complex layers beneath its crust. It's not just a frozen rock, it's alive with activity. And here's the chilling part. This kind of CO2 dominance could mean that 3I/Atlas is older than anything we've ever analyzed up close. Older than Earth. Older than our Sun. It might carry chemical signatures from a star that no longer exists. As one astronomer put it, this isn't just data. This is a postcard from a dead star system. So why is CO2 so strong here? What hidden story is trapped in this frozen traveler? And could studying this object give us the first real chemical map of another solar system? Whatever the answer is, it's locked inside a comet that's passing through our skies right now. When scientists began dissecting the full spectral signature of 3I/Atlas, they realized this comet wasn't just rich in CO2. It carried a molecular cocktail unlike anything ever recorded. James Webb's ultra-sensitive instruments picked up clear signals of CO2, carbon monoxide, water vapor, water ice, cosmic dust, and even faint traces of rare molecules like OCS. These aren't just random ingredients floating in space. They're a chemical blueprint, a story frozen in time. What makes it so strange is the balance between these elements. In a typical comet from our solar system, water dominates the coma, with CO2 and CO playing supporting roles. But here, CO2 leads the show, while water and other volatiles seem to be hiding beneath the surface. That imbalance tells scientists something crucial. This comet likely has a thick insulating crust, a kind of protective shell that traps water ice deep inside, while letting the lighter CO2 escape first. It's like the comet is wearing an ancient frozen armor, slowly cracking as it approaches the sun. Deep within that crust may lie untouched material from a star system billions of years old. Material that has never once been exposed to the heat of any sun. Every molecule Webb detects is a clue to how this traveler was formed. The ratio between CO2, CO, and water isn't random. It points to an environment that was far colder than the one that shaped our own solar system's comets. It suggests a birthplace where ice is formed farther from the star, preserving volatile compounds that would normally evaporate here long ago. What's even more fascinating is how these molecules behave. Instead of a smooth, gentle release, Webb's data shows bursts and spikes, sudden surges of gas, almost like the comet is breathing in and out. Those bursts could be caused by underground pockets of CO2 and CO, sealed off for billions of years, now finally breaking free as the surface warms. To astronomers, this isn't just interesting. It's a window into an alien world. It's the closest thing we have to taking a core sample from a distant solar system without ever leaving ours. 3I/Atlas is essentially leaking secrets from another star system into the void, and Webb is catching every molecule in stunning detail. This molecular cocktail isn't just chemistry, it's evidence. It's a story written long before our sun was even born, preserved in ice, carried across the galaxy, and now unfolding before our eyes. And if these chemical fingerprints are this unusual, what else is hidden beneath that frozen shell? What if its core holds something we've never seen before? The deeper scientists look into the chemistry of 3I/Atlas, the clearer one thing becomes. This comet didn't just randomly form in deep space. It was born in a very specific region of its parent star system, a place astronomers call the CO2 ice line. This is the invisible boundary in a young, swirling protoplanetary disk where temperatures are just cold enough for carbon dioxide to freeze into solid ice. It's farther out than the water ice line, colder, darker, and more stable, the perfect environment for ancient material to build up slowly over time. That's why the unusual chemical mix Webb detected is so important. A dominance of CO2 over water vapor isn't just a curiosity. It's a signature, a fingerprint pointing straight back to where this object likely formed. It's like following a breadcrumb trail across the galaxy. In our own solar system, comets usually come from regions where water ice is abundant. But 3I/Atlas tells a different story. It formed in a colder, more distant zone, where CO2, CO, and other volatile molecules could pile up and freeze while water remained trapped beneath. That makes this object a perfectly preserved sample of a part of another solar system we've never touched. What makes this discovery revolutionary is what it reveals about how planets and comets form in star systems that aren't ours. Protoplanetary disks, the massive clouds of gas and dust that surround young stars, are the birthplaces of everything: planets, moons, and comets. But studying them directly is almost impossible. They're too far, too faint, and constantly changing. But 3I/Atlas brings a piece of one right to us. It's a physical relic, drifting into our backyard, carrying the original ingredients of another planetary system. Scientists believe this comet might have formed billions of years ago, remained frozen and untouched, then got ejected, maybe by a passing giant planet or gravitational chaos, and traveled through the darkness of interstellar space until it reached us. And now, for the first time, Webb's instruments are letting us read its origin story molecule by molecule. This is more than a comet. It's a map of a world we can't see, a direct sample of a distant star's nursery, a clue to how other solar systems build their architecture. If this is what one interstellar object reveals, imagine what an entire population of them could tell us. 3I/Atlas is not just a visitor. It's a messenger from a world that no longer exists in the same way, a frozen witness to the birth of a solar system light years away. The story of 3I/Atlas becomes even more extraordinary when you trace its path through space. This isn't a gentle orbit around the sun like a regular comet. 3I/Atlas is moving on a hyperbolic trajectory, a one-way ticket through our solar system, never to return. It's traveling at an astonishing speed of around 210,000 kilometers per hour, slicing through the darkness like a cosmic bullet. At that speed, it's not just passing by. It's escaping everything. No gravitational pull from the sun, no planetary tug, nothing can trap it. It's a true interstellar traveler. What's even more mind-blowing is where it came from. By carefully reconstructing its path backward, astronomers traced its origins to the direction of Sagittarius, a region toward the center of our Milky Way. That means this object has been journeying for billions of years, crossing star systems, drifting through interstellar space long before humans even existed. The only way something can end up on a hyperbolic orbit like this is through violence, a massive gravitational event that kicked it out of its original home. Picture a young star system with giant planets orbiting in chaos. One close encounter, one gravitational slingshot, and a comet like 3I/Atlas is hurled outward with unimaginable force, flung beyond the reach of its star, and set adrift into the galaxy. That's exactly what seems to have happened here. And now, after traveling across cosmic distances, it's slicing through our solar system, a ghost from another world. Its extreme trajectory gives scientists a unique gift, a clean interstellar sample that hasn't been altered by years of circling a star. Unlike comets bound to orbits, this one hasn't been reshaped, melted, or recycled by repeated passes near a sun. It's as close to pristine as it gets. And its hyperbolic orbit isn't just a number on a chart. It's a story carved into its movement. It speaks of ancient planetary systems, chaotic gravitational dances, and the sheer scale of galactic time. At 210,000 kilometers per hour, it's moving so fast that by the time most people even hear about it, it'll already be on its way out. This is a brief encounter, a flyby from deep time. It came from far beyond, and after a single blazing pass through our skies, it will vanish forever into the void. But before it disappears, James Webb and other observatories are racing to capture every molecule, every flash of activity, every detail of its journey. Because once it's gone, so is a priceless piece of galactic history. 3I/Atlas is not just moving fast. It's carrying a billion-year-old secret, and time to unlock it is running out. One of the strangest and most fascinating things about 3I/Atlas isn't just its speed or chemical signature. It's its unshakable stability. Most comets, once they get close enough to the sun, begin to wobble. The powerful jets of gas shooting from their surface push them off their original path ever so slightly. But 3I/Atlas doesn't flinch. Despite intense outgassing and flaring activity, Its trajectory has shown almost no orbital deviation. It's moving like a solid spear through space, locked on its course with frightening precision. That kind of stability tells scientists something critical about what lies beneath its glowing coma. This isn't a fragile ball of ice barely held together. The data points to a massive, dense, and possibly rigid nucleus, estimated to be between 1.4 and 5.6 kilometers in diameter and weighing more than 10 billion tons. That's an interstellar mountain of ice and rock. To put that into perspective, a nucleus this stable could withstand powerful bursts of gas without budging, meaning it's either exceptionally heavy or structurally more solid than most comets we've ever studied. Some researchers believe its outer layers might be compact and reinforced by a crust of ancient material hardened over billions of years drifting through interstellar space. Others suggest its density could be higher than typical comets, hinting at a different internal composition altogether, something we've never sampled before. What's even more remarkable is that its stability under extreme activity gives us an incredibly accurate orbital path. Unlike Oumuamua, which exhibited strange accelerations that puzzled scientists, 3I/Atlas behaves like a heavyweight champion, steady, predictable, unstoppable. This also means it's likely survived countless cosmic encounters on its journey: radiation, temperature extremes, collisions with dust and particles, yet it remains structurally intact. That alone makes it a treasure trove of ancient information, preserved better than most local comets ever could be. Its sheer mass suggests it formed as part of a massive reservoir of icy bodies in its original star system, then got violently ejected without breaking apart. And now, as it hurtles through our solar system, it carries that intact core like a sealed time capsule. Scientists know that if they can decode its internal makeup, they might glimpse what planetary building blocks looked like billions of years ago in another corner of the galaxy. A comet this large and stable isn't just a visitor, it's a survivor, a relic from a forgotten world, holding secrets in its frozen heart that no telescope has ever seen before. As soon as James Webb's first observations of 3I/Atlas were confirmed, the scientific community moved fast. This wasn't just another comet to study. It was a galactic messenger passing through once in a lifetime. Within days, a massive multi-observatory campaign was launched, uniting some of the world's most powerful instruments. Hubble locked on to capture its visible light structure with unmatched clarity. Swift, with its ultraviolet and X-ray vision, began scanning for energetic outbursts. The Gemini Observatory and ground-based telescopes around the world pointed their mirrors toward the same target. Together, these eyes on the sky created a global surveillance network focused on one object, 3I/Atlas. Why so many telescopes? Because each one sees a different layer of the story. Webb peels back the veil in infrared, revealing the molecules, the gases, the hidden chemistry. Hubble sees the shape and evolution of the coma and tail in fine optical detail. Swift detects high-energy activity that could hint at volatile reactions happening beneath the surface. Gemini and other observatories map how the dust cloud expands and shifts as the comet nears the sun. Each wavelength adds a puzzle piece, and together they build a complete, multidimensional portrait of how this interstellar object behaves. What makes this campaign so historic is the timing. Scientists are tracking 3I/Atlas in real time as it approaches the inner solar system. That means they can watch its entire evolution, from a quiet traveler in the darkness to a roaring, active comet near the sun normally. By the time comets are studied in such detail, their activity has already peaked. But here, scientists are witnessing the ignition process from the very beginning, catching every flare, every molecular jet, every shift in brightness. This synchronized global effort is unlike anything attempted for an interstellar object before. When Oumuamua and Borisov passed through, the world scrambled to catch up. But this time, humanity was ready. Telescopes across continents and in orbit are feeding data back to research teams, building a living timeline of 3I/Atlas's journey through our solar system. And this isn't just about observation. It's about decoding behavior. If we can understand how an interstellar comet reacts to solar heating, we can predict its internal structure, its composition, and how these ancient travelers evolve as they pass near stars. It's like performing a cosmic autopsy while the patient is still alive and moving at over 200,000 kilometers per hour. Every hour of data captured could hold answers to some of the biggest mysteries in planetary science: how star systems form, how comets survive for billions of years, and how material from alien suns might one day seed new worlds. 3I/Atlas isn't just under the watch of one telescope. It's under the collective gaze of an entire planet, and the story it's revealing has never been told before. Even before 3I/Atlas came anywhere near the sun, it started doing something that left scientists stunned. It woke up early. Most comets remain quiet and inert until they cross a certain distance where sunlight is strong enough to heat their frozen surfaces. Typically, that's when water ice begins to vaporize, and the familiar bright coma and tail start to form. But 3I/Atlas didn't follow that rule. It started outgassing far earlier than expected, well before reaching the distance where water would normally react. The reason lies in what's hiding beneath its crust. Instead of being powered by water ice, this early activity is being driven by CO2 and CO, gases that sublimate at much lower temperatures. That means the comet began releasing gas and dust while still in the cold outer reaches of the solar system, a behavior that's rare and deeply revealing. CO2 and CO are far more volatile than water. They don't need the warmth of the inner system to erupt. Just a small amount of solar energy is enough to crack open ancient pockets trapped beneath the comet's surface. The result is a spectacular early show of jets and flares long before most comets even wake up. This early ignition tells scientists something profound about 3I/Atlas's internal structure. It suggests that beneath its insulating crust lie thick, volatile layers, frozen for billions of years, waiting for the faintest sunlight to set them free. It's a kind of cosmic pressure cooker, and as it approaches the sun, those reactions are only getting stronger. Unlike water-driven comets, which slowly warm up and gradually become active, 3I/Atlas erupted like it was ready to speak the moment it entered our neighborhood. That makes it a perfect natural laboratory. By observing the timing, intensity, and composition of its outgassing, scientists can reconstruct how its internal layers are structured. It's like watching a slow-motion X-ray of an alien comet's insides. And because these gases are escaping before water ever starts to dominate, Webb and the other observatories can study pristine material, untouched, unaltered, exactly as it was when it formed around another star. The early activity also gives astronomers more observation time. Instead of a short, chaotic window near perihelion, they have months to track its evolution, capturing how its chemistry changes step by step as it moves closer to the sun. And each of those steps carries clues: how fast the jets flare, where they come from, what molecules dominate. All of it maps the comet's hidden architecture. For many scientists, this early behavior is one of the most exciting parts of the entire mission. It's proof that 3I/Atlas is not like local comets. It's more volatile, more ancient, and possibly more fragile in ways we've never documented before. A comet that wakes up early is a comet with secrets to tell, and Webb is listening to every whisper. 3I/Atlas is not just a comet passing through our solar system. It is a galactic time capsule, a frozen relic that has journeyed across billions of years and light years to reach us. Scientists estimate its age to be between 3 and 11 billion years, meaning it formed long before our Sun, Earth, or even the familiar planets existed. Every molecule trapped in its icy nucleus, every layer of dust and frozen gas, carries a chemical and isotopic memory of its parent star system. These signatures preserve the temperature, pressure, radiation environment, and chemical conditions from a place and time we could otherwise never directly observe. The comet's early outgassing, driven by CO2 and CO rather than water, adds another layer to this story. It reveals how its internal structure, crust, and volatile layering have been preserved for billions of years. The fact that it becomes active far from the sun gives us the chance to watch these ancient materials respond to heat for the first time, providing real-time insight into the behavior of matter formed in an alien environment. Every flare of gas, every widening of the coma, Every developing jet is like opening a page of a diary written billions of years ago, a chronicle of cosmic evolution traveling across the void to tell us its secrets. By combining observations from the James Webb Space Telescope, Hubble, Swift, Gemini, and ground-based observatories, scientists are able to capture a multi-layered, multi-wavelength portrait of this extraordinary visitor. The spectral maps, chemical inventories, and isotopic clues offer a rare chance to compare its materials with comets from our own solar system, testing ideas about how planetary systems form and evolve. In effect, 3I/Atlas is not only a messenger from deep time, but also a laboratory for studying the chemistry and physics of ancient star systems, an interstellar artifact carrying knowledge that would otherwise be forever lost. Watching 3I/Atlas is like witnessing a story written across billions of years and across light years of space, arriving intact in our solar system for the first time. Each observation, each spectral line, each measurement is a message from the distant past, a whisper from a star system we can never visit directly. It is a rare, fleeting opportunity to decode the history of another world, preserved across eons, and delivered to us on a cosmic highway, making 3I/Atlas one of the most remarkable celestial objects humanity has ever observed. The observation of 3I/Atlas by the James Webb Space Telescope marks the beginning of a new era in interstellar science. Until now, interstellar comets were treated as rare, fleeting curiosities, objects that appeared unexpectedly and vanished before we could fully study them. Webb's ability to capture a high-resolution infrared image and detailed spectral map demonstrates that these visitors can now be systematically tracked, analyzed, and understood. This opens the door to a future in which interstellar objects are no longer unpredictable anomalies, but predictable subjects of scientific inquiry. With Webb setting the precedent, astronomers can now design faster detection systems, leveraging survey telescopes and sky monitors to catch these objects early, sometimes even before they officially enter our observational window. Once detected, targeted telescope campaigns can be launched immediately, combining space and ground-based observatories to gather a multi-wavelength, multifaceted view of each comet's composition, structure, and activity. This coordination ensures no detail is missed, from volatile chemistry to coma dynamics, dust grain behavior, and isotopic ratios, all of which reveal insights into alien star systems. JWST's success also reinforces the importance of global collaboration and responsive observing strategies. Coordinated campaigns across multiple observatories, wavelengths, and instruments maximize the scientific return and enable us to capture phenomena that would be missed by any single telescope. This networked approach ensures that when the next interstellar visitor appears, we will be ready to study it in unprecedented detail, building a growing archive of extraterrestrial materials and behaviors. Before you go, don't miss what comes next. Click on the video in the end screen to continue exploring the mysteries of the universe. See more mind-blowing interstellar discoveries. Trust me, you'll want to watch every second. The journey is only getting wilder.